Alright, this is Algebra 2, Chapter 1, Section 1, 2, and 3. Couple sections are pretty definition heavy. Not a lot of math involved, or not a lot of cumbersome math. So 1.1 talks about patterns and expressions, more so expressions and the terminology they're in. They talk about mathematical concepts. First, they talk about quantity, right? Anything that can be measured or counted is a quantity, and the value of the quantity is the measure or the number of the items counted. So, quantity, anything that can be measured, value, the actual number associated with that quantity. Quantities whose value does not change is called a constant. So, definition you might want to know is the concept of a constant. Again, quantities that do not change. So instead of saying quantity, let's just say a number. In essence, that's what it is. Some number or some value that remains the same throughout the calculation. So when I think of an expression x plus 5, that 5 would be a constant due to the fact that it's a number and it'll always be 5. 5 will always be 5. It won't be a situation where 5 is 4. Therefore, we call that a constant. Variable quantities or variables can change. Variables can change. And what is a variable? A variable is a symbol, usually a letter, used to represent some unknown value. A symbol used to represent some unknown value. X, Y, and Z, these things are examples of variables. X, Y, Z, and these are all examples of variables. We don't know what the number is, but we put a variable or a letter in its place to represent that. Numerical expression. So when I do these definitions, you don't necessarily have to copy down my words. You can still copy the book's definition. I just give sort of highlights of the definition that I think is important. So when we talk about a numerical expression, things about a numerical expressions, the first thing that comes to mind is no equal sign. That would be an equation. And people get that confused all the time. So no equal sign. Number 2, you can have one or more constants. And the last thing is you can at least one operation. At least. So we have, for something to be considered a numerical expression, no equal signs, one or more constant, at least one operation. So you could also say at least one constant. So 5 times 3. My operation is multiplication. I'm multiplying these two guys. Or 7 minus 4 times 8, right? Two operations, subtraction, multiplication. I have three constants, or three numbers. These are examples of numerical expressions. And then algebraic expressions builds upon that. Again, no equal sign. You can have numbers, or you can say constants, or variables. At least one operation. And we talk about operation. Operation is multiplying, dividing, adding, subtracting, right? So in the case of algebraic expression, the book has 3n plus 5. Right? We have numbers, we have variables, and we have operation of adding. Or the book has 8x minus 2, the difference of 8x and 2, plus the product of 5 and n. Right? So we have three operations, right? Subtract, well, four operations, but three types. Multiplication, subtraction, adding, multiplication, right? That is algebraic expression. I looked ahead at some of their problems, and it's really not that difficult. Just recognizing the patterns and building upon it and guessing what the next pattern is. Things that you guys can do. Input and output. Again, I have every confidence that you guys can do things like that. Properties of real numbers. All right. Again, another definition heavy section. So we have types of numbers. Starts off with natural numbers. And we have an example of natural numbers: 1, 2, 3, dot, dot, dot. Right? That means it goes on forever. So the first condition is no fractions, and decimals. That's the first condition. Second condition, positive numbers. And the third condition does not include 0. Does not include 0. Alright, no fractions or decimals. Positive numbers does not include decimals. So starting at 1. 1, 2, 3, 4, and up forever and a day. Then we have something called whole numbers. Alright, whole numbers is very similar to natural numbers with just one caveat. Here's an example. 0, 1, 2, 3, dot, dot, dot. Very similar to natural numbers. Matter of fact, I'll say the first two that are identical. No fractions or decimals. So I'll put fraction slash decimals. Okay. Positive numbers. And third condition does include 0. Does include 0. Okay, that's the conditions of whole numbers. Okay. Third condition, or third type of numbers in a real number system, uh, is called integers. And integers, examples of that: -2, -1, 0, 1, 2, dot, dot, dot. Actually, in both directions. So dot, dot, dot. And remember, those three dots mean that they go off infinitely in that direction and infinitely in that direction. First two are the same. No, well, the first one is the same. So no fractions or decimals. This one does have negative numbers, so numbers can be negative or positive numbers. And the last condition is that it does include 0. It does include 0. Okay? Those are integers. Then we have the next condition, which is rational numbers. Rational numbers. And rational numbers is the first set of numbers where you can have fractions and decimals. So it can be whole numbers. It can have fractions. And it can have decimals. But here's the caveat with the decimals. Oh, an example. The book has -1/2. Actually, do the dot, dot, dot. So dot, 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 -1/2, negative, let's say 0, 0, 0.22213, dot, dot, dot. Whole fractions, whole numbers, fractions, and decimals. Here's the caveat with the fractions, or the decimals. The decimals have to be terminating or repeating decimals. And to refresh your memory, a terminating decimal would be something like 0.5, right? It stops at the tenths place at the number 5. Or repeating decimal could be 0.3333, right? It goes on forever. Or we can call it 0.3 bar. Alright? And those are situations where those are the two conditions that the decimals have to be. They have to be either repeating or they have to be terminating. And lastly, it does include 0. So rational numbers, whole numbers, fractions, or decimals. The decimals could be either terminating or repeating, and it does include 0. Okay. And then we have the last set of numbers. If you notice, each set of numbers sort of build on the other. Natural, whole, integers, rational. Irrational here on this part, on this chapter, chart rather is all the way to the side. And that because there's a situation here where it doesn't necessarily build. And the reason why it doesn't build is because of this. So, irrational. Examples, dot, dot, dot. Negative square root of 3, 0, 1/2, pi, dot, dot, dot. Again, can be whole, fraction, decimal. The difference here is that the decimals here now the decimals here have to be the decimals have to go on forever. And non-repeating. So, two examples of this is I use the number pi. Pi goes on forever. I leave 1 forward. Blah 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 blah. I use negative square root of 3. So any square root that's not a perfect square is an irrational number. Any square root that's not a perfect square is an irrational number. They can be positive or negative, and does include 0. Okay. Okay, so those are classifying numbers. Graphing them on a number line. Again, I don't think I necessarily need to focus too much on this. I think you guys are pretty good at graphing on a number line. Just from my experience, if I was to graph this, I have square root of 3, negative 1.14, and 1/3. So the square root of 3, if I was to graph this on the number line, first thing would be negative 1/4, 1.4 rather. Then the next one, let's put a 0 here. This next one would be 1/3, and then the next one would be square root of 3. Right? Pretty straightforward. Same thing with ordering rational numbers. We know that this symbol is called an inequality. And this inequality here means less than. This inequality means greater than. This means less than or equal to. And this means greater than or equal to. So when we order rational numbers, things to keep in mind that you might have forgotten, but I don't think so. The more to the left something is on the number line, the smaller the number is. So number negative 5, negative 4, negative 3, This is -3, -2, 1, 0, 1, 2, 3. The more to the left something is, the more negative something is. The more to the right something is on a number line, the more positive something is. So since -2 is to the left of -3, then I can say that -2 is less than -1 because -2 is more to the left. And then if you're more to the left, you're more negative. Likewise, I can say that 2 is greater than 3. I'm sorry, 2 is greater than 1. Because 2 is to the right of the number line, therefore 2 is more positive than 1 on the number line. Properties. Alright. Good times. Alright, so properties. The first one they talk about is the closure property. I'm not going to harp too much on the closure property, but what it says is that if I start off with a number and add the same type of number to it and it ends up with the same number, then under the closure property is closed. So what does that mean? If I have a real number, so 1/2, and so this is a real number, and I add another real number, let's say 1/4, then my answer should also be a real number. So 1/2 and 1/4 gives me 3/4. 3/4 is also a real number. So then I would say that this is closed under the closure property. And it should also work with multiplication. 1/2 times 1/4 is 1/8. That is also a real number. So it checks. That's the closure property. Now again, I'm not going to harp too much on it because I don't. The one that I care more about is the other ones. So commutative property of multiplication and addition. So I write it at this, commutative property of addition. All that says is that if I have some two numbers and I rearrange the order, then they're the same. The commutative property of multiplication says the same thing. If I have two numbers and I rearrange the order, they will be the same. So 1 plus 2 is equal to 2 plus 1. 2 times 4 is equal to 4 times 2. So those are examples of the commutative property. Then we have the associative property. So the associative property of addition says that if I have 3 or more things that I'm adding, and if I have the associative property of multiplication, and if I'm multiplying 3 things, it doesn't matter which 2 I add first, they're going to give me the same answer. So if this was 1 plus 2 in parentheses plus 3, that's going to give me 1 plus 2 plus 3 in parentheses. Alright, 3 plus 3 is 6, 5 plus 1 is 6. Likewise, if I have 1 times 2 times 3, that's going to equal 1 times 2 times 3 in parentheses. They should be the same. 2, 3, 6 is 1, 2, 3, 6 is 1. So again, this is all review, so I'm going pretty fast. Associative property of addition. Identities. There's identity of multiplication, and there's an identity of addition. And the way that that works is that for something to be called an identity, and I always write it like IDT with a plus sign. There's the IDT with the multiplication sign. For something to be an identity, the number that I start out with has to be the same number that I end up with. So if I have A and I add it with some number, that number has to be such number such that when I get my final answer, that answer is also A. So the only thing that I can think of that would give me A is 0. So any number plus 0 is always going to equal itself. Same thing over here. I have some number and I multiply it by something, and it gives me the exact same number. That number is 1. So A times 1 will always equal itself. These are called identities. Okay. Inverses. There's a additive inverse and a multiplicative inverse. So additive inverse and multiplicative inverse. What the additive inverse says is that if I have some number and I add its inverse, then I should always get 0. So 4 plus negative 4 equals 0. Multiplicative inverse, if I have some number and I multiply it times its reciprocal, I'll always get the number 1. So 4 times 1/4 equals 1. So that's additive inverse and multiplicative inverse. Distributive property. What the distributive property says is that if I have some sum or some difference and I multiply that sum or difference, then I have the sums of the products of whatever's being multiplied. Or the sums of the differences. So whatever's being multiplied on the inside is being multiplied on the outside. So if A is multiplying to B, A is multiplying to C, the plus sign carries over. There's going to be A times B plus A times C. If I have two things that are being subtracted, A times B, the minus carries over, and A times C. Distributive property. And again, I'm not going to it pretty fast because, well, you guys have done this before. So if you look at got it for A, so this is for A. We have 3 times the sum of G and H plus 2G is equal to 3G plus 3H plus 2G. And they want to know which property that is. This is an example of the distributive property. This sum inside G times G plus H is being multiplied by 3 to give me 3G plus 3H, so this is the distributive property. For B, I have A plus three plus negative A, and they probably want me to solve this and to show my steps. So first thing I'm going to do is rearrange this a little bit. And I'm going to have a plus negative a plus 3. And what I did there was I used the commutative property of addition to rearrange the order. And remember, it says by rearranging the order, it doesn't change the final answer. The next thing I'm going to do is I'm going to put brackets around the a plus negative a. I'm going real detailed step by step, by the way. Some of you guys might skip that step. By doing this, I'm able to use the associative property of addition that says that I can add any two or things in order first and still get the same answer. So in this case, I choose to add the first two terms. A plus negative a gives me 0. 0 plus 3. I got there because of the additive inverse, which says that if I add the inverses, a and negative a with each other, I'm going to get 0. And then 0 plus 3 is 3. I got that because of additive identity, which says any number plus 0 is itself. So, first step, I took these parentheses off and I moved the negative a closer to the plus a, positive a, and I did that using the commutative property of addition. Then I was able to put brackets over the a and the negative a due to the associative property of addition. Then I was able to say that a plus negative a is 0 because of the inverse property of addition. And then I'm able to say that 0 plus 3 is 0 because of the additive identity. Okay, and that's section 1-2. Again, I'm going pretty fast, but it's all of this is pretty review. Straightforward review. All right, algebraic expressions. All right, so we talked about what an algebraic expression was in chapter 1-1. Algebraic expressions are not equations, right? They have at least one number and or variable, and you have at least one operation. Adding, subtracting, multiplying, and dividing. Okay, it says which algebraic expressions model the word phrases 2 times the sum of A and B. So we have the words and we're supposed to find out what the actual numeric expression or algebraic expression is. So when you see something that says 2 times the sum, or if you see something that says 2 times the difference, this word, the sum, that automatically tells me that I'm putting something in parentheses and I'm adding it. I'm putting something in parentheses and I'm adding it. And it says it's the sum of A and B. Whatever is first is going to be the first thing that I put in the parentheses. Whatever is second, this is going to be the second thing I put in the parentheses. And it says it was 2 times the sum. So when I think of sum, I think of parentheses. Here I think of A plus B. And since it says 2 times the sum, I think of multiplication, and I'm multiplying. So I'm multiplying some parentheses that has that has A and B in it, and it says the sum, so I know that I'm going to add whatever that is. And that is identical to H. So it would be H. More modeling. I'm looking at number 2, got it. And it says you had 150 books, but you are spending $2 a day. What algebraic expression can you do to model this particular situation? So, what do I have? I have $150. I'm told that I'm spending. So if I'm thinking of looking at the word spending, I think of subtraction because it's being taken away. And it says I'm spending $2 each. When I think of each, I think of multiplication. And what am I multiplying? I'm multiplying it each day, right? So each day. So I can put a variable d for day. I know it's each is multiplication, and it's multiplying each day. So I have $150, and I'm spending $2 each day. I have $150, and I'm spending $2 each day, or 150 minus 2d. Okay. Evaluating these things. Hopefully we can evaluate some stuff. So I'm going to go straight down to the 3a. Got it. They give me 2 times the sum of x squared minus y squared over 3. They tell me that x is 6 and y is negative 3. So I'm going to substitute 6 for x, negative 3 for y. So this becomes 6 squared minus negative 3 squared. 6 squared minus negative 3 squared. The negative 3 is in parentheses. Remember, this negative in front of 3 has nothing to do with this subtraction in front of the y. Those are two different negatives or two different minus situations. We also should know that if we have an even power, anything that's squared or to the 4th or to the 6th or to the 8th is going to give me some positive number, right? A negative times a negative is a positive. So when I rename this, I have 2 PEMDAS tells me that 6 times 6 is 36, and 3 squared is 9. Then PEMDAS says I do parentheses next. 36 minus 9 is 27, and then 27 times 2 is 54. Alright, so I wrote my expression. I substituted 6 and 3 for its corresponding variables. 6 squared is 36, negative 9 squared is 9. Remember that that minus and that negative 3 have nothing to do with each other, so it's still a subtraction inside of the parentheses. 36 minus 9, which gives me 27, and 27 times 2 is 54. The reasoning question says, will the value of the expression change if the parentheses are removed? Well, let's see. So instead of saying two times the sum, or the difference rather, x squared and y squared, we're going to say 2 times x squared minus y squared. 2 times x squared minus y squared over 3. Then we'll do our substitutions. It's going to be 2 times 6 squared minus, negative 3 squared, and that's going to be over 3. PEMDAS again tells me to do the exponents first. There is no parentheses, so okay. It's going to be 2 times 36 minus 9 over 3. Running out of space. That gives me 2 times 36, which is 72, minus 9 over 3. 72, I'll put this up here. 72 minus 9 equals 63. And 63 over 3 equals 21. So, does removing the parentheses affect the final answer? I would say emphatically, yes, it does. By removing the parentheses, we change the order of PEMDAS and what we multiply and stuff first, thereby changing the answer. Okay. Other writing expressions and stuff. I actually like this one, looking at it earlier. So here's what they did, which I kind of like. So I'll go to number 4. So in basketball, they talked about the terms of scoring in terms of what they are. So we have 1 point, a basket. If you make a basket, it's worth 2 points, right? So we have, let's use X for a 2-point basket. I'll just say 2-pointer. We have a Y for a 3-pointer. And let's say Z is for 1 free throw, and the free throw is worth 1 point. So let's say 1 free throw. Alright, so X is a 2-pointer, Y is a 3-pointer, and Z is one free throw, worth 1 point. They are telling me well, first setting it up, I know that in terms of points, X is worth 2 points. So 2 times X. I know that a 3-pointer is worth 3 points, 3 times Y. And I know that free throw is worth 1 point. So a basket is 2 points, so 2 times the number of baskets. 3-point baskets is worth 3 points, so 3 times a 3-pointer. And then a free throw is worth 1 point, so a free throw is the Z times the 1. We are told that we have 10 2-pointers. I'll put 2P. We have 5 3-pointers. And we have 7 free throws. So those are basically the number of baskets. So we will have 2 times 10 plus 3 times 5 plus 1 times 7. And then that will give me the total number of points that I've had in all. So this is 20 plus 15 plus 7. So this is 35 plus 7, which is 42. So this person went off and scored 42 points. Good job, whoever that person was. Okay. Definition of various things within a expression. So an expression could have multiple things called terms. So a term is an expression that consists of uh, either a constant, or variable, at least one. And the operation has to be multiplication. Uh, you can have some division. The only thing about it is, though, you can't have a variable in the denominator. Hate this stylus. You can't have a variable in the denominator. I'll just write AVAR. So let's go through some definitions of that. Let's look at 5x. This 5 would be my constant. And my constant is always going to be some number multiplying the variable. This would be my variable. And the operation is multiplication. I can also have 1/5 x. And when I think about division, what I'm really thinking about is fractions. So I need to be more specific about that. So I have 1/5 x. I could have x over 5, where 1/5 is my constant, x is my variable, and I'm still multiplying. I'm multiplying the fraction. You could also say that I'm dividing by 5. You can break up these things into multiple terms. Multiple terms are separated by either the addition symbol or the subtraction symbol. So we have here that the book gives us negative 4ax plus 7w minus 6. We have one term here, two terms here, three terms here, right? This term has a constant of negative 4 and two variables, and they're all being multiplied, separated by an addition symbol. Then we have a constant 7 multiplying the variable w, separated by an addition and a subtraction symbol, and then we have a 6 here all by itself. And this would be called a constant term. And a constant term is just a constant or number all by itself, not multiplying anything. Although technically you can say it's multiplying something if you wanted to. But we won't go there right now. Like terms. Like terms are terms that have the same variable raised to the same power. So the book gives us 3x squared plus 5x squared plus 9y cubed z plus 2yz minus 4y cubed z. So these guys are like terms because they both have the variable x and they both have the variable x raised to the second power. These powers are the same. these guys are like terms because they both have the variable y and z, and the variable y and z are, or the variable y rather, has the same power. They're both raised to the third, and this z has a power also. They have the power of 1. And then this 2yz is all by itself. It doesn't have a like term to compare it with. Even though it has a y and a z, this y is raised to the first power, and the z is raised to the first power. So the z's are the same, but the y isn't. And all it takes is one of those variables not to have the same power for these to be considered not like terms. Definition of subtraction. So to subtract something is to add its inverse. So if I'm doing a minus b, subtraction just means to add its inverse. So we're adding, and the inverse of b is negative b. So adding its inverse. Definition of division. This is basically saying that a fraction is division. A divided by b is equal to a over b. Yay. The condition being, of course, that b can't be 0. The denominator cannot be 0. Always. We can't divide by 0. It is undefined. We can also say that a is being multiplied by 1 over b as well. Distributive property of subtraction. It's the same thing like distributive property of addition. If I have some number and I have some parentheses, everything in the inside can be multiplied by whatever's on the outside. So a is being multiplied by b. Since I'm subtracting in the parentheses, that parentheses carries over, and I'm multiplying a times c. Multiplication by 0, or multiplicative property of 0. Any number times 0 is itself. Any number times negative a equals the inverse. So negative 1 times a equals negative a. So number-wise, I could think of negative 1 times 4 equals negative 4. Or I could think of it as two negatives. Negative 1 times negative 4 equals positive 4. Why? Because positive 4 is the inverse of negative 4. So any number times a, any number times negative 1 equals the inverse. Opposites of sums. So remember, inverse means opposite. What is this? How do I get rid of it? Okay. What just happened here? How did I? Oh, gritty. I don't even know what I did. Okay. You. Can I get rid of that thing? I don't know. Can I clear it? That's going to annoy me. Alright. Opposites of sum. So I have two things that's being multiplied. Hello. Why can't I reach you? Oh, goody. Oh, let's do this because it's getting on my nerves. Alright. Thank you. That was silly. Alright. So, opposites of the sum. If I have two things that are being added in here, and I multiply it times a negative number or negative 1, then I have the opposites. And I have the opposite of a and I have the opposite of b. So negative a plus negative b is the same thing as saying negative a minus b. So that's the opposite of a sum. Opposite of a difference. If I had this same negative, but instead of a sum, I have a difference in parentheses, I'm going to have negative a minus negative b, which is the same thing as saying negative a plus b. And what the book likes to do is, since they don't like the negative a in front, they rearrange it and call it b minus a. Then we have opposite of a product. If we have a product a times b, and we're multiplying it times negative 1 or an opposite, same thing as saying negative a times b, which is negative a b. Or we can say that it's a times negative b. The negative is interchangeable. I could put the negative in front of a or the negative in front of b. And then opposite of an opposite. If I have a negative in front of a negative number inside, that's a negative times a negative. That gives me a positive. Right? A negative of a negative, or an opposite of a negative, is positive. So negative, negative 5 is 5 positive. Alright, simplifying terms and expressions. Oops. We have negative 4j squared minus 7k plus 5j plus j squared. The only like terms that I see is the j squareds. We have a negative 4j squared and we have a 1 in front of that j squared, so that's 1j squared. That gives me negative 3j squared minus 7k plus 5j, and then this would be my final answer. There's nothing else that I can simplify. Notice that it doesn't say to solve anything. This is 5a. They're asking me to simplify 5b. I have, ooh, this looks like fun. I have negative 8a plus 3b plus 10 times the difference of 2a minus 5b. Alright, so I'm using the distributive property. I'm distributing this negative across. So this is opposite of sums, which gives me negative 8a minus 3b. And then I use the distributive property here, and I'm distributing the 10. Here I distributed the negative. That gives me 20a minus 50b. I see if there's any like terms. I see like terms for the b's. They're the same variable raised to the same power. And I see like terms for the a's. They're both a's raised to the same power. So negative 8 plus 2 is negative 6. So negative 6a. Negative 3, whoops, that's a 20a, isn't it? So this should be 12a. And then negative b, 3b, and negative 50b gives me negative 53b. And then that would be simplified. Okay, and that is this section, section 1.1, 1.2, 1.3. I hope you guys have a great rest of your